Section 8.5, Probability Distributions with Expected Value. If we were to purchase a raffle ticket, what would we expect our payback to be? A random variable is a function that assigns a real number to each outcome of an experiment. A table that lists the possible values of a random variable together with its corresponding probabilities is called a probability distribution. A shipment of 12 computer monitors contains 3 broken monitors. A shipping manager checks a sample of 4 monitors to see if any are broken. Give the probability distribution for the number of broken monitors that the shipping manager finds. So we want to find the probability of 0, 1, 2, or 3 broken monitors. So let's start with the probability of 0 broken monitors. So we're going to use our formula. We want to have the 3 choose 0 times choose the leftover 9 choose 4. So we have 12 computers all together. So 3 and 9 is 12. The 3 contains broken monitors. So we want to first choose broken monitors for none because we're looking for the probability of none. That means that there would be 4 leftovers that do not have, because we're checking 4 monitors. We would have 4 that are not broken. So all over the total number of options we have, since we're choosing 4, is 12 monitors, choose 4 of them. Alright, so I know that 3 choose 0 is equivalent to 1. So anything choose 0 is equivalent to 1. We're going to multiply that again using our formula. So I'm going to have 9 factorial on the top over 9 minus 4 factorial on the bottom, 4 factorial, which is equivalent to, well, anything times 1 is itself, so I'm not going to worry about the 1 anymore. 9 minus 4 is 5, so 5 factorial, 4 times 3 times 2 times 1, and then 9 times 8 times 7 times 6 times 5 factorial, so that I can get rid of the 5 factorial. I could get rid of the 4, the 2, the 8, since they're all common. So if I were to multiply all of those together and then divide by 3, I would end up with 126 over, and now I have to do 12 choose 4. So on the top we would have 12 factorial over, I suppose I don't even need this parenthesis here. So 12 factorial over 12 minus 4 factorial, 4 factorial. So that's the same as, 12 minus 4 is 8, so 8 factorial times 4 times 3 times 2 times 1. The top would be 12 times 11 times 10 times 9 times 8 factorial. We can get rid of some items here, and if I were to multiply all the way across and divide, I would get 495. And I can reduce that fraction down, so reduce fractions if possible, and we would end up with 14 over 55. Okay, so now I need to repeat this for the probability of finding 1. But we've already found our denominator, so we don't need to worry about that. So the probability of finding 1 defective 1. So I'm going to choose, of the 3 defective, I now want to have 1 that's defective. And of the 9 remaining, 3 are not going to be defective. And then still we have 12 choose 4 on the bottom. So anything choose 1 is the number of the anything. So 3 choose 1 is we have 3 options. 9 choose 3. On the numerator, thinking ahead, just kind of, hopefully by now you're able to skip some steps. We would end up with 9 minus 3 is 6 factorial on the bottom, and then 3 times 2 times 1. So on the top I would only need 9 times 8 times 7 times 6 factorial. Knowing that I can get rid of the 6 factorials. So if I were to multiply then 9 times 8 times 7 and divide that by 6, multiply by the outside 3 here, we would get 252 over. We already know that 12 choose 4 is 495. And if we reduce our fraction, we will get 28 out of 55. So reduce your fraction again. We now need to do the probability of 2 defective ones. So I'm going to choose, of the 3 defective, I want 2 of them to be defective. And of the 9 remaining, I'm only going to have 2 that are non-defective over 12 choose 4, which again we already know what that is. Verify above that on your own that 3 choose 2 is also 3. We've done that a few times now. And then we'll have 9 choose 2. 9 choose 2 is 7. So we'll have 7 factorial times 2 times 1. And on the top, so then on the top we would only need to go to 7 factorial. And then again on the bottom we already know that that's 495, so we don't need to do anything there. So we can cancel out some items. Using our calculator we can multiply 9 times 8, divide that by 2, and then multiply by the outside 3 to get 108 over 495. And reducing that down gives us 12 over 55. Finally, one more. We want to find the probability of 3 being defective. So we are going to have all 3 of our items be defective, meaning we're going to have 0 that are not okay all over our same denominator. So we know that 3 choose 3 is equivalent to 1, so 4 choose 4, 5 choose 5, whatever it might be is equivalent to 1. I also have 9 choose 0, so I'd only have 9 options. You could verify using the formula over 495. This is equivalent to 9 over 495. And when I reduce that down, we end up with 1 over 55. So notice how we have the denominator of 55 in each one here. That's not always going to be the case. You're not always going to have the same denominator. So note that that could be different. It's just coincidence that it happened this time. Now it's asking us to draw a histogram to represent the data in the table. So if I were to make my above numbers into decimals so that we could create a histogram, so here we'd have 0, 1 defective, 2 defective, 3 defective. We end up with decimals, so on the left-hand side, I'm going to go by tenths. So if I were to take 14 and divide it by 55, I would get about 0.25. So I'm going to draw a histogram all the way across so that the entire 0 area is represented by about 0.25. So if I were to take 28 and divide it by 55, we would end up with about 4.5, 0.45 or so. So in the 1 section, I will color this to represent the probability of 1. Turning the probability of 2, so 12 divided by 55 is just over, I believe, 2/10. And then finally, the probability of getting 3, 1 divided by 55 is very teeny tiny, so it's going to go down here. So find those decimals so that you can properly put in the shaded regions. Using the same information from the last problem, what if the inspector decides to choose only 2 monitors to inspect? Give the probability distribution chart. So what if they only choose 2 monitors instead of 3? We still need to find the probability of 0, which would be, we're choosing 3, but only 2 to be inspected. So we're going to choose 0 first of all, and multiply that by the remaining 9, choose 2 that are not defective, all over 12, choose 2 instead of 12, choose 4. So anytime we're multiplying or choosing 0 from a number, it's equivalent to 1. I know that 9 minus 2 is 7, so 7 factorial times 2 times 1. And then above I can only write 9 times 8 times 7 factorial to help us simplify a little bit, knowing that our 7s can disappear. So if I were to multiply all the way across, 9 times 8 divided by 2 would give me 36 over something here. So now I need to do 12, choose 2. 12 minus 2 is 10, so we can stop at 10 factorial. So then 2 times 1, so 12 times 11 times 10. So our 10s cancel. And if I did 12 times 11 and divided it by 2, we would get 66. Reducing our fraction, we would get 6 over 11. Oops. So let's choose, find the probability of finding 1 defective. So we're going to find the combination of 3 that are defective. We want 1 of them to be. Of the 9 remaining, we're going to have 1 that's also okay. And then our total amount of choices is 12, choose 2, which we already know is 66. We also know that 3, choose 1 is 3, and 9, choose 1 is 9. So we'd end up with 27 over 66, which reduces down to 9/22. So here's an example where the denominators aren't the same. And then finally, let's have 2 that are defective. So of the 3, I want all 2 of them to be defective. So therefore, 0 will not be defective of the remaining 9. And then our denominator is still the same. 3, choose 2, we've done this many times, is equivalent to 3. 9, choose nothing is equivalent to 1. And we know the denominator is 66. So 3 over 66 is equivalent to 1/22. All right, I want you to practice making a histogram to represent the data in the table. So pause the video and then come back and we'll check it out together. So we'll turn the above into decimals. And we're creating a little area here. So this should be 1, and then this should be the area of 2. We can go up by tenths again. If you chose a different scale, that's fine. All right, so if I were to take 6 divided by 11, should give us right above about 0.55. That's an awful line. So then we can shade that area in. If we did 9 divided by 22, it's about 4.4 and a little some. It's looking like our probabilities are decreasing the more we're trying to have defective. And then 1 divided by 22 is 0.05, so very teeny tiny area down here. So your histogram should look similar to mine. Prepare a probability distribution when 2 dice are rolled and the total of points is recorded. So the total points is the same as the total number of total value. So what is the probability? And we're going to do this the regular probability way, back to section 8.1, so Introduction to Probability. What is the probability of getting a 2 when I roll 2 dice? Oops, Well, there's only really one option. It's snake eyes, so 1 in 1. So there is a 1 out of 36 chance of getting 2 dice, of getting a 2. What is the probability of getting a 3? So our options are 2 and 1, 1 and 2. That should be it. So there are 2 out of 36 options to get a 3. And if I reduce that down, that's the same as 1/18. What's the probability of getting a 4? Well, we could get 3 and 1, 1 and 3, or 2 and 2. So we have 3 out of 36, which is the same as 1/12. Now notice that our numbers are increasing here. As you know, that's not going to be the case as we continue this chart. But this will get you started on number 2 of your homework. So follow this same pattern to determine the remaining chart for number 2 of your homework. Prepare a probability distribution when 2 balls are drawn from a bag in which there are 4 white balls and 2 black balls. The number of black balls is the one that's counted. Let's start with the probability of getting 1 black ball. So, of the 2 black balls that I have, I want one of them to be the one I choose. Therefore, the remaining white balls, I'm going to end up having to choose one of those, ideally, because I have only 2 balls that I can grab. And then I want, of the 6 balls I have altogether, 4 plus 2 is 6, I'm going to choose 2 of those balls. Alright, so we know that anything choose 1 is that anything. So 2 times 4, so 2 choose 1 is 2, and 4 choose 1 is 4. Over, and then I need to determine what 6 choose 2 is. 6 choose 2 is equivalent to, 6 minus 2 is 4, so 4 factorial times 2 times 1. So on the top I can stop at 4 factorial, knowing that I'm going to be able to get rid of some options. 6 times 5 is 30, divided by 2 is 15. So this is equivalent to 8 over 15, which I cannot reduce. And this will get you started on number 4 of your homework. So you only have to finish off the probability of 0 and the probability of 2 based on how we started here. Suppose the random variable x can take on the n values x sub 1, x sub 2, x sub 3, etc. Also suppose the probabilities that these variables occur are probability of 1, probability of 2, etc. respectively. Then the expected value is to multiply the x value by its probability and then add them all together to find what our expected value would be. So if the probability of earning $399 is 1 out of 2,000, we will take $399 and multiply it by its probability. Add that to, since it's a positive 79, we'll multiply that by 79 times 1 over 2,000. Since we have another positive 19, we'll multiply 19 by 2 out of 2,000. And here we have a negative, so now we want to subtract 1 times 1996 over 2,000. So 399 times 1 is 399. Divide that by 2,000 and we'll get 0.1995. Plus 79 divided by 2,000 is 0.0395. 19 times 2 divided by 2,000 gives us 0.019. Minus 1996 divided by 2,000 is 0.998. So using our calculator, if we added all these decimals together, we would get a negative 0.74, meaning we would expect to lose 74 cents in this game. Now it doesn't tell us how much we purchased the ticket for, but these are the probabilities of winning these certain amounts. So, each day, Donna and Mary toss a coin to see who buys coffee for $1.20 a cup. One tosses and the other calls the outcome. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find Donna's expected payback. So, if there's two options when we toss a coin, heads or tails. So I could have heads, tails, tails. And you'll see why I chose two of them here in a second. So every day, if I flip a coin, I could have heads or tails. But while it's flipping, the caller either has the option of choosing heads or tails. So we really have four options. We could have heads, 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 tails, tails, heads, tails, tails. So since when it's tossed it's heads and the caller wins heads, then we win. If the result of the tossed coin is heads, but I called tails, we would lose, so we would not win. If, similar to if tails is flipped, but I called heads, we would not win. And if tails is flipped and tails is called, we would certainly win. So since there are only four options, the probability of getting each option is 1 out of 4 options. Okay? So if I win, Mary would have to buy coffee for $1.20 a cup. So my first option here, we would have $1.20 times 1/4. In our second one, we would have to subtract $1.20 because we didn't win. So subtract $1.20 times 1/4. Again, we're not winning in our third option, so subtract $1.20 times 1/4. And then finally, we win in the last one. So if we multiply and then add and subtract all these together, you'll notice that we have exactly two items that are positive, and those exact same two items are negative. So if you multiply and add them together, we should get a 0. This means that any expected value of 0, like we got above, is called a fair game. So it's really anybody's game, and nobody would really win or lose because it would break even in the end. And this concludes section 8.5, probability distributions and expected value.